welcome to the last section of our workshop, which is on funding and scientific progress. And quite interestingly, this session is composed mainly only by submitted papers. So it's nice, we have contributed papers. And the first one is from Matteo Michelini, Dutch-German affiliation, Technical University of Eindhoven and Ruhr Universitat Bochum, in collaboration with Javier Osorio from Madrid. So 20 minutes and then 10 for questions.
Hello, everybody. So the talk you're going to see from me is actually probably quite different from the ones you've seen so far, because this is a talk of a philosopher of science, and my co-author is also a philosopher of science, but we do work with computational models, right? So when we were thinking about it to submit to this conference, we thought, oh, it would be very, very cool to actually hear some feedbacks from people working in quantitative studies, and to get some ideas on what are your thoughts about theoretical modeling in philosophy. So that's the idea of my talk. So the topic is about diversity in evaluative criteria, enhances scientific inquiry, epistemic landscape model. So I don't know how many of you are familiar, but there's a rather large branch of philosophical literature, which is called computational philosophy of science, that does theoretical modeling for understanding and improving science. And these are mostly theoretical models, and they try to ask questions of what is the best communication protocols between science, what is the best way to deal with evidence for scientists, and they try to be normative in the argument. So that's the kind of aim that they have. They try to understand science and possibly understand how we could make it better. But they do it mostly without looking too much at empirical data, right? So the reason why I'm here, I'm trying to pitch this to you and get to hear some feedback about what to do with it. In particular, this kind of literature considers science as an instance of problem solving. So the idea starts from Kuhn, right? So the idea that scientists basically explore solutions and they try to find the best solution for a certain problem. However, part of this assumption, part of these models has to deal with the idea that each scientist has the same evaluative criteria for what counts as a good solution, right? So scientists look at a solution, a possible solution, and think of a solution as a possible theory to solve a problem, or as a possible model to represent a phenomenon, or as a possible research approach to study a certain question. And the assumption that is in science usually is that each scientist looks at this possible object and evaluates it in the same way, right? So they all assign the same value to the same object, scientific object. Now, our idea, this is not our idea, but what we start from is from the fact that actually scientists often look at the same solution, sure, but they evaluate them differently, right? So they assign different values to each solution. So the question is whether or not this situation, so the fact that scientists have different evaluative criteria for what counts as a good solution, may slow down sciences. So can these slow down scientific inquiry, scientific success? Okay, so for the overview, we start with the introduction, then I'm going to say something about evaluative pluralism, so having different evaluative criteria. Then I'm going to present briefly the model results and conclude. So we call evaluative pluralism a situation in which there's a certain degree of difference in the way scientists evaluate the same scientific objects, right? So again, theories, possible models. And there's been lots of work in philosophy of science about these, philosophy of science, also history of science. A good example is from Chang, 2012. He has his book on Is Water H2O. He claims that scientists have different epistemic values, and this leads them to adopt different solutions, right? A similar case is the one made by Douglas, right, about non-epistemic values. Right? We know that in order to do science, you need non-epistemic values, and sometimes scientists may have different ones. So again, they may evaluate solutions differently. Certain times, the reason why people evaluate the same scientific object differently may only come from the fact that they have different goals, right? So think of devising the perfect model, right? Depends on what kind of phenomenon you want to target, you want to study, right? So there's an example from Nicholson. She says that when there's a research started about finding the best photosynthesis model, scientists were approaching these search with different goals in mind. Someone wanted to actually apply the knowledge about photosynthesis for agricultural chemistry. So they were looking at these kind of models in completely different perspective, right? So they wanted different things from this model. And because of that, they evaluated model differently. Now, of course, evaluative pluralism comes into degrees, right? So there's certain communities in which there's a lot of diversity in evaluative criteria, certain others in which there's less. And what we ask today is what is its impact? Are periods of evaluative pluralism productive? What is the most suited communication protocol for this kind of community? So community in which there's a high degree of diversity. And the question, of course, is also, am I better off interacting with people with different standards or with the same ones? Of course, there's some people, Chang and others, claim that actually evaluative pluralism may benefit scientific inquiry, but of course, it's also reasonable to think, well, if we actually have different evaluative criteria, and if we look for different things, then maybe we can just benefit less from learning from each other, right? Because if Eugenio looks for something satisfying certain aims, I'm very unlikely to benefit from what he finds, right? Because that's good for him. It may not be good for me. Okay, so the way we want to answer this question is by using an agent-based model. So by trying to understand how scientists with different criteria actually could learn from each other, and they could benefit from each other if they can, right? Good, for the model. So a solution is a combination of components. So now we go into the idea that there's many solutions and scientists evaluate them, right? So they explore them and they evaluate them. Solution is a combination of components. And the idea is that the fitness of a solution, so how good that solution is, depends on the average fitness of each component. And in particular, the fitness of each component depends on the component itself and on k-1 other component. This is a so-called NK model. Maybe now you feel a bit lost, but I hope you're not. But the idea is just that solutions are complex. So if you change one component, that does not only affect the value of that component, but also the value of many other ones, right? Because solutions are complex. And of course, we want to say that, well, the fitness of each component is not the same for everybody, but each scientist assign a different fitness to each component, right? That's our starting assumption, that there's different criteria. Particularly, we use a very basic parameter D, probability, right? So, and we assume that the probability D is given from the beginning of the model, and it tells us what's the probability that scientists agree on the evaluation of a certain component, right? So they meet a certain component in the solution, and they may think, oh, this has a value of, say, 0.8, and they all agree about it, or they may all think that it has different values. And fitness values are always drawn from a probability between 0 and 1. When scientists agree, it is the same for everybody. When scientists disagree, it is different from each scientist. So if you have a diversity of 0.1, say, for example, it means that, well, most of the time, on most of the components, scientists will agree on this evaluation, right? Whereas if D is very high, they will mostly disagree about it. Good. So then we put some behavioral rules, again, very theoretical, very abstract, but we think that they are the most basic ones that we could use in this situation. So a local search rule, so a way for agents to actually look for new solutions, right? And the idea is to say, this one, you start from a solution, whatever, say X, based on many different components. And in order to explore other solutions, you have to change one component at a time. You change one component, you land on a new solution, and you compare the new solution with the previous one. If you like it, you stay there. If you don't like it, you go back, right? So that's local search rule. And it happens, this is quite crucial, I'm gonna say why later on, in 2 steps, right? So we assume that it takes some time for scientists to actually go on a solution, explore it, understand it, and then maybe go back, right? So it's, say, we're talking in terms of scientific inquiry. It may take you, I don't know, 1 year to figure it out whether a new solution you've tried out is actually good for you or not, right? And if you like it, you remain. If you don't like it, you go back. And then there's social learning rules, right? So scientists learn from each other. They copy each other's solution if they like it. We have 2 possible rules. The systematic sharers, the situation in which everybody knows everybody's present solutions at the moment. So say a community in which every scientist share with everybody else what he's working on, and people listen to him, know it. And we have a situation in which there's sporadic sharers. So people only learn about few solutions of other scientists. This is represented in a way in which basically at each step, I only know what another random scientist is working on. So way less information flow. Good example. So that last bit, right? So how we evaluate epistemic success of a community, right? So I said that our starting question was, well, we want to understand whether or not diversity evaluative criteria is going to slow down inquiry. We need a measure for epistemic success. And we say that we call it the multiple satisfaction criteria, and we say that the success of a community corresponds to the average success of each individual in the community. Okay, so we take the average of the success of each individual. But of course, the success of an individual is the fitness of the solution the individual is working on, right? So the solution that she is working on at the moment, based on her own evaluative criteria, right? So I look at a solution with my own evaluative criteria, and I decide how good is that, and that's my fitness. And then to look at the fitness of the whole community, we do the average, very basic. And this allows us to answer as a scientist, am I better off interacting with people with different standards or with the same needs? Good. So just a brief recap, scientists explore solution. At each step, they can either explore a new one or decide whether to come back or to remain. And then in each turn, there's also social learning. So they may decide if they know that someone else has a solution better than theirs, they could completely jump there, right? So say I know that Eugenio has a very good solution that I really like. I basically adopt his solution. His mechanism of copying his solution. Good. This can be thought as an exploring of a landscape. I don't have too much time to go into this, but if you want to hear a bit more, I'm happy to do it later. So results. So what we start from is from monist communities. So we call monist communities communities which there's no difference in evaluative criteria. And these are results that are known to the literature, so it's nothing new. We just basically replicate. I don't know if you're familiar with this. It turns out that, okay, so first of all, on the x-axis, the number of steps of the simulation. On the y-axis, the community fitness, right? So the epistemic success of the community. And then the lines are how the fitness changes. Then on the K represents the complexity. So a lower K, a less complex problem, a higher K, a higher complex problem. Now, the idea that you can see here is that sporadic sharers, so communities with a very small information flow, perform better in the long term. So they reach higher success, they reach higher fitness. Whereas community with systematic sharers, they share it all the time and they copy each other all the time if they have the possibility. They perform very good in the beginning, but then they actually are outperformed from the other kind of communities. As I said, this is nothing new. This is known in the literature. Why is this so? Because agents start from different locations, they start from different solutions, right? And they can explore what's around those solutions. But of course, and so the social learning, so copying someone else's solution can be useful because you can benefit from the exploration, the solutions that have been explored by other people. But at the same time, it is detrimental as it decreases the exploration potential. So what does this mean? It means that if you copy, so if I copy Eugenio, sorry, I'm going to take you as an example, Eugenio's solution, then we're going to find each other in the same solution, and we're going to start exploring the same set of solutions, and this decreases our exploration potential. We're going to explore less, basically. So monist community benefits from some learning, but slow learning. An example where we can go back in the questions if you're interested. So what changes if you have diversity in evaluative criteria? Now, the first pattern I would like you to notice, so the plot is the same, right? But this time on the different sets are different diversity coefficients. The first thing I would like you to notice is that the yellow line actually becomes to be higher than the purple line when you increase the diversity. So what does this mean? It means that communication, so systematic communication, systematic sharing becomes more and more beneficial, fruitful for communities, the more diverse in terms of evaluative criteria these communities are, right? So while we would like to have a slow learning in monist community, we actually like a lot in terms of what's best to have a lot of copying each other and a lot of sharing when we're talking about more pluralist community, so community with a high degree of diversity. Good. So why is this so now? You may wonder, right? So the idea is that social learning is less dangerous. And because convergence can be broken up. So let's go back to the example, right? So me and Eugenio are on the same solution. If we have the same evaluative criteria, we're going to end up exploring the same solution around the starting one, because we're going to like the similar ones, right? So the route that we can take, the path of exploration that we can take is the same one. If we have different evaluative criteria, we can take different paths. So convergence on the same solution is not as detrimental, right? So it is less detrimental. And at the same time, this is also very important, and also a term that we kind of came up with. So this idea of proxy diversity. So whenever scientists share all the time what they are working on, scientists with diverse evaluative criteria are more likely to profit from each other. Let's go back to the initial solution, right? So suppose that someone else has different evaluative criteria than me, then most of the solutions she's gonna like are gonna be not really good for me because we have different criteria, right? So I'm rather unlikely to find what she finds good to be good for me. But if she shares, very good, yes, if she shares all the possible exploration that she does, I'm way more likely to find something that is actually good for me. Because she may not share, she may end up working on a solution that is actually suboptimal for her, but that turns out to be good for me. We call situations of this type situations of proxy diversity. So, not diversity, sorry, proxy serendipity. There's a mistake there, my bad, proxy serendipity, okay? So the idea that someone explores a solution completely useless for her, but that turns out to be useful for someone else. So proxy serendipity. Sorry, I fucked up the only interesting thing. So, and so because of these, the success of evaluative pluralist community depends on the possibility to communicate, right? So the possibility of benefiting from proxy serendipity. And this is only to give you an idea of why this is the case. So again, we have the same plot as before, but this time the plots above have a tweak. So the plots below are the same one you already saw. The plots above are a situation in which scientists only share the solution they are proud of. So they only share the solution they find extremely good for themselves, right? If that's the case, then we cannot have cases of proxy serendipity. And because that's the case, well, as you can see, systematic sharing is not that important anymore, right? So it's actually always suboptimal, regardless of what's the diversity degree of communities. Good, so the last thing that I want you to notice, though, before going to the conclusion, right, yes, is that actually, not only evaluative pluralist communities fare better with systematic sharing, but systematic sharing diverse community also fare better than monist ones on any possible communication protocol. So like this, you can see, right? If you look, for example, at the case for diversity being 0.3, you can see that the community fitness is, well, consistently higher than the community fitness of the monist communities. Right? So what does this mean? It means that, well, actually having different evaluative criteria may slow down inquiry, maybe, because maybe in the beginning it slows it down, but in the long run, it's going to actually benefit inquiry quite a lot. It's going to actually allow scientists to reach a way higher scientific success. And why is this so? Again, because basically scientists can benefit from each other's mistakes, from each other's unsuccessful investigations, from cases of proxy serendipity. Right? Good. With these, I'm going to basically conclude. So what do we make out of this model? So it's some kind of theoretical argument for why evaluative pluralism can be, of course, epistemically very successful, right? So, and it not only tells us how, that it can be successful, it also tells us how it can be successful, right? So by having a lot of communication, and this is against other models that have proven that for monist communities, well, communication is not that nice or needs to be lower. We show that actually if the communities are diverse, we want some consistent sharing. And also requires in particular, not just sharing of the solutions you like, but sharing of unsuccessful investigation. Again, proxy serendipity. Good, okay, this one is correct, very nice. Then at the same time, it also highlights a concept, which is the concept of diverse evaluative criteria, which is something that, well, it is rather known in philosophy of science, and we do often talk about the fact that scientists have different standards, they have different values. but in the literature about diversity in problem solving is something usually put a bit aside. So there's this famous book by Scott Page, and he talks about diversity of preferences, which somewhat could be similar to this, as something actually that is just bad for problem solving, and we have to solve it before we actually get into the matter, or something along these lines, right? So we actually highlight that this kind of diversity could actually be very nice. And it is a combination of cognitive and social diversity. Okay. Now, for the empirical challenge, which I'm happy to discuss with you, maybe you have some insights about this. Of course, how do we connect these with quantitative empirical data? So there is some possible real data calibration to be done, right? So how often do scientists share the data? Is it actually happen that scientists share what we called in this model unsuccessful investigation, right? Is there even a way to look at this? Because we don't know, I'm going to be honest, we don't really know about it. And at the same time, there's some anecdotal evidence about the fact that scientists disagree about values, but what's the extent of this, right? And then lastly, can we actually see if a situation in which there's disagreement about values do improve the productivity, right? So that would be another question that we were discussing. How do we do it? And of course, again, we have very little clues. So I guess this is it. Thank you very much.
Thank you very much also for the nice picture, Jens. So Alicia, and then Marco.
Thank you so much. I really like this talk. And I want to say, I can't help thinking that this has something related to the so-called reproducibility crisis.
Mm-hmm.
Can you speak a bit about that in light of your research? Because
how would you connect it?
okay, so I could be wrong then, so I'm sorry, but you said that different scientists have different evaluative models for the same object.
Yeah,
right?
Yeah.
Which means you can have the same data set and somebody has a different idea about how to evaluate it, right? So that means it's reproducibility, like you said, it's not really a crisis of reproducibility. Based on what you said, it's better actually to have, it's fine if you have this data set and other models or other ways of evaluating it.
Yeah, cool. Very nice connection. Thank you very much. So I think there's one caveat to be done in the beginning. We want to be sure that we're talking about legitimate evaluative criteria, right? So as long as we're talking about the legitimate evaluative criteria, so we don't want some pseudosciences to sneak in because that would be bad. But as long as we're talking about legitimate difference criteria, I agree with you, right? So this work could be taken, of course, as a theoretical argument, so no normative claim for now. Of course, we need the other part, but could be taken as a theoretical argument to be in favor of, maybe disagreement about evidence is just fair. It's just what we get from having different criteria, and there's nothing to worry about.
Why should we reproduce all the time?
Well, maybe we could reproduce, but getting different results is not necessarily bad. I mean, of course, now this is I'm making a very out of context claim, so take it with a grain of salt, of course, but I'm trying to stretch what this model could say about this. Thank you, though. Appreciate it.
Thank you very much. I really enjoyed the talk. A lot of things out there. Epistemic landscape used to be my king, but when I was younger, so I'd like to see them through going. An objection, though, that might also apply somehow to something I was discussing with Cassidy. It would be nice if we have infinite time for reading, and but we don't. Apparently, I mean, I don't, and that's an issue. So in order to enjoy the benefit of proxy serendipity, we will need infinite time to read, as far as I see. I mean, if we only publish what we deem successful, that will be, let's say everybody publish one paper per year, then we have 30 papers in this room for a year. But if we publish also what we deem unsuccessful, if you ask me my unsuccessful, there could be 300 papers, and many of them could be deemed unsuccessful for a good reason. So we'll have 300 rather than 30 papers. So I was wondering whether in accounting for in considering the benefits of proxy serendipity, you were also considering the risk of paper overflow and something like that, because otherwise there's a passage still to be done, I think. Was it clear?
Amazingly clear, very nice. I didn't think about this, but it's actually on point. Thank you very much. So I think that this is also, say, we could call it the cost of, well, pluralism, right? So pluralism requires, I mean, at least pluralism a la Chang, right? So active normative pluralism, right? That's the idea. We want to have, we would like to have many scientific systems, but we don't want to have them not talking with each other. We want them to talk. We want them to talk with each other. So I totally get your worry, and I think it's a fair worry. And I think it is of course hidden inside the idea of proxy serendipity, but it comes not only with this. It comes with requiring people to work with different frameworks at the same time and interact with one another, right? So I think it's a very good point, but I think it's also already somewhat into the starting assumption more than actually in the development of the model, although of course proxy serendipity is a good case of this. Yes, thank you.
Thank you for the fascinating paper. So I don't know a lot about this literature, so I might misunderstand some of your key points. But, my question is this. So imagine a panel of scientists which is called to evaluate a research proposal. Some of these panels do have criteria. For example, one common criteria is impact. Is this potentially impactful or not? So if they disagree regarding the impact of a certain thing, would that be related to your evaluated diversity?
Absolutely, I would say so, yeah.
Because that's not necessarily about the epistemic value. Sometimes it's just the impact clearly has also a lot of, think about the medical sciences, for example. So would this work? Could this be important for treating patients that otherwise have a disease that we don't have a drug for? Okay.
Yeah.
So if your answer is yes, like you seem to say, then my suggestion for your potential calibration is that you can try to get data regarding the evaluations in panels, and maybe you could have field diversity.
Yeah.
And in different fields, I would expect that you may have some variance regarding whether people agree or give the same score to the same potential impact of the same thing. Because you always have more than one reviewers reviewing a single application. You could have a sort of a measure of disagreement. It's just...
Yes, amazing. Thank you very much. We did find some evidence about it, but it's very, very, I guess for now, I don't want to say anecdotal, but like, so there was this paper about bisphenol A, which is some kind of weird chemical, and scientists were asked to evaluate specific research approaches. And they clearly evaluate them, each aspect of the research approach rather differently, right? So they would agree on certain parts, they would agree on the value of maybe the sample, I don't remember, but so there would be some degree of disagreement in the way they evaluate research approach. So yes, thank you very much. I think that would be very nice, and it's a good. Of course, the question though, if I have to think about it, is also whether or not here we're talking about different epistemic values, or we're talking about some error that is included in the way scientists evaluate papers, right? So because I may have a different value from you, maybe I value a lot simplicity, while you value a lot, say, I don't know, coherence with other theories or something like this. And we have a different epistemic values, which translates in a different criteria, but then we also may sometimes not understand perfectly the paper, right? So that doesn't have necessarily anything to do with our different values. It's just a misunderstanding of the paper, right? So it is also a matter of trying to differentiate these two things, right? So one thing is how actually criteria depends on values and depends on goals, and how actually accurate we are in evaluating papers. But yeah, thank you very much.
So thank you very much. Thank you again.